In this video, we're going to talk about establishing the relationship between what an area collector and an integral, and we're going to see if we can't start to bring calculus into this and stop just talking about geometric shapes and Riemann sums. So I've given you a function f of x. The function g of x finds the area of f of x. So I'm going to call it an area collector. So you can see here I've written g of x is equal to the area from -3 to x of f of t dt. Now, the f of t dt, the t here, that variable is really unimportant. We sometimes call it a dummy variable. The basic idea here is that if I plug in, let's say, like g of 0, that means I'm finding the area from -3 to 0 of this function. I should not be using the same variable. And since I'm doing this in reference to the x-axis with g, finding the area from -3, I said, to 0, I just shouldn't be using the same variable. I didn't have to pick t. I could have picked anything. Please do not let that trip you up here. That is just a really minor notational piece we have to include. Now, I'm going to try and draw the graph of g. So let me get a starting place here. I'm going to start on the left side, g of -3. Good to know where to start. So you notice the g of x is defined as the area from -3 to x. So if I'm plugging in -3, I have to plug that in for x right here. Well, the area from -3 to 3 is 0. So that's where my graph's going to start. Okay. Now let's start drawing. You notice up here we're finding the area. This is all positive area. So as I move along, I'm collecting positive area. That means g just keeps getting bigger and bigger. So g should just be going up and up and up, like that. Well, at -2, we start collecting negative area. Well, I was collecting positive area, so I was getting bigger. If I collect negative area, I start having to subtract area off or add a negative area. So now I'm decreasing. And I'm going to decrease. I'm adding negative area all the way to 3. So let me draw that. I'm going to try and not go off the page. We're going to go down and down and down. Negative area. We just keep collecting negative area all the way to 3. Well, now we begin collecting positive area again. So that will increase our area collector. Our area collector will start going up like that. And of course, we run out of room. Now, what I hope you see here is a relationship that I think we suspected already, and that is you've got this red graph. Okay, it's going up. It's got a maximum. Notice the black graph, F, changes from positive to negative. Here we've got a minimum, right? In the black graph, we changed from negative to positive. Every time the red graph was going up or increasing, the black graph was positive. Whenever the red graph was decreasing, the black graph was negative. It certainly seems like the derivative of g is equal to f. Now, this is a pretty important relationship, okay? Because you look up here and you say, well, if I took the derivative of g prime, a derivative is very algebraic. So if I take the derivative of this side and it just comes out to be f, then the derivative must cancel the integral out. Well, to cancel something out, they have to be inverses. The inverse of a derivative is the antiderivative. And I think this is a relationship we suspected based on what we talked about before. Remember our position function? And we said, well, position, if I want to get velocity, I take the derivative of position. And we've been talking about how do you get back. And I think people have started to say, well, geez, if taking the derivative brought me down, wouldn't taking the antiderivative bring me back up? This relationship is starting to kind of seep into our minds, I think. But it's not a proof, and it's not for sure, and that's what I want to show you next. But this is a very important relationship, for sure. Let's look at a kind of a simple proof of it. Okay. So here's what I want to establish. I want to establish that if I take the derivative of g, I end up with f. So if I take the derivative of this function and the derivative of this, the derivative cancels the integral out. And if I can prove that the derivative cancels the integral, then the integral must be the antiderivative. Meaning, to find the area, integral means area, I find the antiderivative. Okay? I'm going to go all the way back. All the way back to when we first started talking about derivatives. G prime of x is equal to the limit, as h approaches 0, of g of x plus h minus g of x all over h. Remember that? All the way back to the definition of a derivative. Now, what we always did with that was we actually would plug x plus h into our equation. So, g of x plus h, my integral, a, remember, just some value, just some, starting point for my area collector. On my previous slide, it was -3. But I'm going to go from a to x plus h. So, I have a limit as h approaches 0 of the integral from a to x plus h well, g of x was given to us. G of x is just this integral right here. So, just substitute that in. We're still all over h. Now, I want you to think about this for a second. I'm going to go kind of to the end here. I'm going to call this x plus h. I'm going to call this spot right here x. Okay. Well, if I found the area from a to x plus h, I'd start over here and I'd have all of this area. Okay, I'm going to try and have all of this area right in here. If I find the area from, like in this second integral, just from a to x, I'm just going from here back. So the difference between the two, you take the big area and subtract the little area, is simply this little sliver right here. When you take the big area and subtract the little area, this is what you're left with, is this little sliver. Well, that's the integral from x to x plus h. Oop. F of t. Still over h, we're still taking the limit as h approaches 0. Okay, but notice that simplification occurs because the big area minus the littler area leaves us with the area in between. Well, I want to think about this now. I'm going to estimate this with a rectangle. Okay, and I'm actually going to use a left-hand sum for this. As we talked about, the best way to get a great approximation is small rectangles. At a certain point, they have the same limit. And again, we're taking the limit as h approaches 0. So at some point, whether we're taking a left and right-hand sum really won't matter. But I'm just going to choose a left-hand sum. Okay, so it's a rectangle. I'm just going to sketch a simple little rectangle right here. Okay, it's that rectangle that I'm drawing. It has a base of h and a height, well, of the function f of x. Okay, I'm going to run out of room, so I'm going to draw that on the other side, I think. Okay, it's got a height of f of x. And again, that's the left-hand sum. If you chose to do right, it would be the f of x plus h, but again, it won't really matter. Well, why I did that is because I can approximate this, and as h approaches 0, the approximation becomes the actual area. I can approximate that kind of red bubble thing by using a rectangle. Base, oddly enough, with denoted with h, base multiplied by height. Okay, I'm just going to put an arrow up. That's just the area of that little sliver that was left. That's all over h. Limit as h approaches 0. And look what happens. The h's cancel, and I'm left with just f of x. Well, that's what I was trying to establish. I was trying to establish that if I took the derivative of g here, that the integral would disappear and I'd be left with the function f. And what that tells me is that to make an integral disappear, I took the derivative. Those two things must be inverses of one another. This is the fundamental theorem of calculus, part 2. This idea that we can use the antiderivative to find area. Okay? Let me do one quick example of how we could do this. Let's say we wanted to find the area of x squared from 1 to 3. Okay? So now, before we'd use rectangles or we'd put it into our calculator and use f and ant. Now we use the antiderivative. So we raise the power, divide by the new power. I'm not going to put a plus c. I'll explain why in a second. Okay. And we're going to plug in 3 and 1. This line means evaluate at. So we've got the antiderivative, and we're going to evaluate at 3 and evaluate at 1. Okay. So if I plug in 3 to this, 3 cubed is 27, 1/3 of 27 is 9. And if I plug in 1, I just get 1/3, like that. So remember, back to this idea of an area collector. Here's the value of my antiderivative, my area collector at 3. Here's the value of my area collector at 1. How would I find out how much area is between them? I subtract. So it comes out to be 8 2/3 or 26/3. So to find the area of a curve, we find the antiderivative, evaluate at both endpoints, and find the difference. And that'll do it. And this is how we'll use calculus to find the area under a curve. Why we didn't need the plus c, well, there are two reasons. One is kind of just an algebraic, if I put plus c, when I evaluate at 3, I get 9 plus c. When I evaluate at 1, I get 1/3 plus c, and you'll notice the c's are going to cancel out, and they always are. The more, kind of theoretical, conceptual reason we don't need it is I'm not saying, hey, what functions have a derivative of x squared. I'm saying I want the area under x squared. I don't need a family of functions who all have the same derivative. I actually want the area under this function. So I'm not looking for you to give me a general antiderivative. I'm looking for you to just use the antiderivative to give me an answer. So that's why you don't need the plus c from a conceptual reason. They'll cancel out is the reason algebraically you won't need a plus c.